also related to magnetized, so actually you were switching the gears at the right moment. So what I'll talk about is about possibility of anomalous physics in the magnetospheres of magnetars. So it's about some physics that we were working on for several years, and actually only like about a year ago we finished the draft and finally published this. So it's a very interesting idea, basically along the lines that there is an interesting anomalous physics that typically is considered in the context of heavy ion collisions in condensed matter physics, and you all know that by the name of Chiral magnetic effect. So is there a possibility of some anomalous effects of similar type in magnetars? So this is something that has been on my thoughts for a long time until we realize where it really works. In fact, we were trying to do it both in the context of black holes and in the context of magnetars. And I'm obviously presenting only the magnetars, and perhaps you could guess the reason it doesn't work near the black holes. So what are the magnetars? Basically, those are pulsars, or if you wish, the neutron stars, which are known to be the laboratories of dense matter. But I'm not going to talk about that dense matter that exists inside of the neutron stars, so you would have to decouple from that idea right away, because we'll be talking about the space outside of the neutron stars, outside of the magnetars, in the magnetospheres that forms there. So, of course, you know that the idea of those neutron stars is relatively old, nearly 90 years old. They were discovered pretty much like 30, 35 years afterwards, and there are many interesting features about the neutron stars that I'm not going to talk about, but just to put it in the context, there is a wide range of angular velocities, or the period of rotation in this particular case quoted here, a very large range of rather strong magnetic fields that could exist in the pulsars. And because of that, we could also have some observable phenomena, such as pulsating signals that we see and associate with those neutron stars. There is a very, very wide range of observed candidates of pulsars, and usually people in astrophysics, they like this kind of phase diagram where you plot those stars in the plane of the period and the period derivative. And if you consider this graph, actually it tells a lot of information. Not very reliable information, I might emphasize, but a lot of information about the characteristic age of the stars that was actually highlighted with those dashed blue lines, spin down luminosity, so how much energy it loses, also like there in the red, you could also see that the magnetic fields could be estimated. All of those are very rough estimates. Don't take them at the face value, but you could get some guidance. And in fact, in this corner, you will find some stars which are presumably having extremely large surface magnetic fields. So those magnetars, they actually have very interesting physics. And I will not be able to even touch a % of that knowledge that exists, but I want to talk briefly about the outside of the magnetars. Outside of the magnetars could be modeled with different types of models, and on the market there were a number of them proposed. So one of them is the naive and the most simplest model. So why don't you take that basically outside of the star you have a plain vacuum, no charge density, no currents. This is the so-called vacuum dipole model. And roughly speaking, what you have is a magnetic dipole sitting completely inside of that star, vacuum outside, and it's spinning. So that kind of model, from the point of electrodynamics, you could actually solve it pretty much with almost perfect precision. Inside of the star, you have relatively large conductivity of matter. Because of that, you basically have no local electrical fields. So in the lab frame, of course, you will have non-zero electric magnetic fields, but in the local frame, you have to have zero electric field. Then you could find what kind of boundary conditions are required, what kind of a solution to obtain, and you will find the configuration outside of the star immediately from that suggestion. So basically, this was done back in the day, so it's a well-known solution. I didn't even write it down because it's kind of long and not instructive at all. The interesting thing about this, if you consider the boundary conditions on that star, you will find something interesting. there is a non-zero charge density sitting on the surface. In fact, substantial amount of charge density. And from that charge density on the surface and, of course, essentially vanishing electrical field inside, you will be able to figure out that the electrical field on the surface is enormous in this model. And that is actually a signature of inconsistency in the calculation, because if you have such electrical field, in fact, you will rip off charges from the surface. You will always have something electromagnetic in the surface. With such fields, you will rip them off. They will start moving along the magnetic field lines. So this is kind of illustrating it. They pull up from the surface. They move along the magnetic field line. The magnetic field line is not a straight line. It's actually curved. As a result, you will start produce curvature radiation. That curvature radiation goes through this strongly magnetized medium. And actually, in a magnetic field, it's the mean free path of that photon is relatively short. And what happens is it's so short that it goes maybe meters or so and basically creates electron-positron pair. And in fact, you will produce pairs and pairs and pairs in the presence of that magnetic field, because each and every one of them starts moving in that curved magnetic field, creates curvature radiation, and it's an avalanche of the plasma produced. So basically, assuming free vacuum outside is inconsistent, in fact, you will always produce a ton of those charges. They will essentially create magnetosphere outside. So that's basically the bottom line that I wanted to say. So in fact, slightly better model, and this is not exact model, but it's kind of one of the accepted zeroth approximations of the models of the magnetosphere, is the so-called rotating magnetosphere model. So in this model, what is the big difference is really the fact that magnetosphere is highly conducting as well. You have essentially the same condition that the electrical field in the local frame is vanishing. So you could find the electrical fields in the lab frame. Of course, from that relation, you will find the electrical field proportional to something cross B, which means that the parallel component of the field, and I'm saying parallel to the magnetic field, will be vanishing. You could also find the velocity of the charged particles if they are in that plasma, and of course that plasma consists of zillions of particles that are charged. They will be drifting according to the standard E cross B. And of course, if you write down that expression for the field, you will find that there are two components to the drift velocity. One of them is nothing else but the rigid rotation with the star, and the other one is sliding along the magnetic field lines, kind of like a bead on a wire. That's roughly speaking the picture what we have. So the configuration will be in the so-called steady regime, but it's not a static regime. It's very important. The charge will be constantly flying along those lines out. You could find that, in fact, this magnetosphere has to be charged locally with that charge density. Again, it follows from that field. You substitute, find that there is the so-called Goldreich-Julian charge density that must be self-consistently present in this rotating plasma to have everything self-consistent and in agreement with this assumption. So this is the ideal sort of zeroth order approximation to the model of magnetosphere. Unfortunately, it's not perfect, because if it were, we would have contradictions. So there is a relatively simple way of understanding the contradiction. If the magnetic field in the star is evolving over time, it will be diminishing over time, then you cannot actually assume that this E parallel equals 0 is always enforced. So that's a simple bottom line message that I want to give here without going into further explanations. What that actually means, that there is a specific mechanism how this is happening. In fact, that electrical field E parallel almost always with high precision 0. But in order to have that, you need those charges, and in fact also, if you consider carefully, currents that are consistent with the solution I presented. And that is not always possible, because you need the source of those charges and the source of those currents always present. And they're always flying away. And in fact, in order to have that, there is one relatively simple resolution that has been proposed back in the 70s, that in fact you have to have some gaps opening in the magnetosphere. Generically, what it means, you kind of rip up at some point that magnetosphere, and it basically opens up very quickly. and basically that's the region with the vacuum. So those gaps can form at different locations. I highlighted some of them schematically on this diagram of a pulsar. They are intermittent, so basically they are not happening at some super regular intervals. Basically they happen, close, that's how they would happen. The gap size can be estimated, but when it forms, you will appreciate that essentially these particles, they are moving nearly with the speed of light, and therefore the gap opens typically as fast. Of course, as it opens, it generates a potential difference in this vacuum. That's electrical field that is forming in that region, and of course it will grow quite rapidly, and of course at some point it will be so large that in fact it will have to create electron positive plasma that will fill out that gap. So essentially that's in 2 words what will happen. Notice that it is not the Schwinger production that is happening here due to the electrical potential. I'll show you the values of those. They are not large enough. What will be happening is the flux of the photons, radiation from around this gap, from the rest of the magnetosphere, they will go through this window, through this vacuum, with some potential. In fact, they will create relatively easily electron-positron pairs. Now, in the rest of the talk, I will concentrate primarily on the regions near the polar cap because I want to concentrate the regions where the magnetic fields are the strongest. And of course, the fields will be decreasing with the distance as 1 over r cubed. So the estimates and the physics, as I said, of the formation of the gaps is known since the 70s. So it was estimated that depending on the strength of the magnetic field, rotation, angular velocity, and the size of the star, this size is really entering, roughly speaking, in this case, because I'm going to consider close to the polar caps. That gap could be on the order of meters. So this is for the magnetic field of 10 to the 14 Gauss, but you could recalculate for other values. So roughly speaking, from meter to maybe like 30 meters in size. You could also estimate the value of the electrical field that is forming in that gap. And as you could see, this is what I was promising to tell you, that this field is much, much smaller than the critical value of the field. So it's 8 orders of magnitude smaller, so no Schwinger production is realistic in this case. But what is realistic is the formation of those electron-positron pairs due to the flux of penetrating photons, and they will become on-shell particles creating electron-positron pairs. Now, how the formation of the gap forms and how it evolves, there are some simulations. So in 2 words, essentially, you will see that you could form the gap with non-zero potential that will, the gap is forming right here. This is the Goldbach-Julian density, approximately 1 in those units. And when the vacuum forms, you form that essentially 0 density. And you see it grows, and then something starts to happen. That's basically electron-positron pairs starts to evolve, and eventually you end up with the same equilibrium conditions. So this is simulated using some plasma simulations. So that's roughly speaking what happens. Now, if we consider that we have such regions with relatively large electrical field on macroscopic scales, it is interesting to explore the question about the anomalous physics. Because, you know, if you have E dot B present in vacuum, something interesting will happen. And that's about what I'm going to discuss. Again, the fields in units of the critical values, they're always small. I didn't write the same in terms of the B critical. It's also sort of comparable to 1 or less than 1. Yes, here the critical value of the field. And of course, you could say that this is already larger than the critical. And of course, those are smaller. So I'm going to consider all possible cases. Now, if you have E dot B, as I said, you will create chiral charge in the system. So I'm going to consider the simplified version. Essentially, it's sufficient in vacuum when you have nearly homogeneous system. You will have the production of the chiral charge due to the anomaly. Chiral anomaly, that is relatively large for the fields that we will consider. But one has to be careful because there is also the effects due to non-zero mass of the electrons. Positrons in the plasma, and they, of course, will be working against the chiral anomaly. So they will be washing it away In fact, when you reach the stationary state, you will get the value of the charge determined by the anomaly, proportional to eta b, but inversely proportional to the rate at which it washed away, obviously. So if this rate is very large, of course, you will get almost nothing. So that rate actually is estimated. It's not super well calculated, but estimated reasonably well in the limits of not very, very high temperatures, relativistic regime, or ultra-relativistic regime. I will be concentrating actually on this regime because this is valid up to about 10 MeV, which is what I need for the magnetized. So it is important to understand if there is a chance for something interesting to see how quickly things happen. So one of the things that you need to estimate is how long it takes for that gap to form. Remember, it's meters or so. It forms at the speed of light, roughly speaking, so that's how long it takes. Very, very short time, right? Now, the time scale for the chiral charge production is actually determined by the rate at which it's washed away. Because essentially that stationary regime is achieved as quickly as this T star inversely proportional to gamma. If the gamma is very large, it will be very quickly saturated, but to a very small value. If gamma is small, it will be developing longer, but it will reach larger values. Anyway, for those values that we have in realistic plasma, it's actually almost instantaneous compared to the times of existence of that gap. So basically, I could really consider that that charge is created at any moment due to the existence of the gap, maybe even at the very, very last moment before it closes. So it doesn't really matter. And of course, that's an important thing because I have to make sure that I have enough time to produce the chiral charge in the system. So how much of the charge is produced? You could estimate. I gave you the formula and put here the numbers. So basically, you could calculate that that is relatively small, but our QCD standards, right? But that's what it is. And you could calculate what is the corresponding chemical potential. It's very small. Of course, the temperatures on the order of 1 to 10 MeV, maybe closer to 10 MeV or so. But anyway, it's a very small number. So you might say, what's the big deal with this number? So here there is some table. You could calculate it for different fields, for everything modified. I will not concentrate too much on this, but I will say that the values here seem to be small, even compared to the electron mass. Now, what are the implications of this? Is there any physical observable we could see and relate to this? Well, one of the things is that when you have chiral asymmetry in the system, in the plasma, then you may have chiral magnetic effect. So the chiral magnetic effect I will not explain because already several people did. In simple terms, we will have a current proportional to the chiral chemical potential, which I estimated for the situation that I have. So what will be the implication in this plasma? The implication will be that it will produce an instability in that region of the gap where this chirality was produced, and immediately after that gap closes, you will have a plasma with mu5 non-zero, and that has physical implications. The physical implication is that the current that you have in the system is given by the combination of the regular ohm current plus this chiral magnetic effect current. It modifies the Ampere's law because that current will enter this equation here. If you rewrite it using the expression for the electrical field from this expression, you will get some relation. You could take the curl and find a self-consistent equation for the magnetic field. So the details are straightforward. It's basic physics. I don't want to concentrate too much on them. But if you look at this final equation, you will appreciate that there are some interesting solutions. The easiest way to find the solutions for this equation is to look in the form of the helical modes. So the helical modes are, by definition, the modes that satisfy this eigenvalue problem. Curl of a magnetic field is proportional to the field itself. This is an example of such a field. Roughly speaking, you could think of it as circularly polarized light moving in the direction of the magnetic field. One circularity will be helicity plus, the other will be helicity minus. So if you try to search for the solution in that form, this is the equation. You will find the corresponding frequencies. And then if you look carefully at this, you will find something unusual. So I'll use an approximate relation, same result, but I'll consider the approximation when sigma is large and consider the expansion in 1 over sigma, because it's easier to see the result. The same is true for the full expression. I just think it's easier to see it here. The most important thing is that here there is one mode which could have positive and negative imaginary part, depending on the value of the wave vector. So the wave vector is small, there will be a growing mode. So first of course mode is nothing super interesting. It's the decay of magnetic field due to conductivity. But the second mode is very interesting because of this plus sign when I consider the condition that the momentum is small. And that means that there is an exponentially growing mode in the system. This is nothing else, of course, but the chiral plasma instability that people considered in other applications, and I'm just repeating the same statements. So in the context of pulsars, I could find this value of the cutoff momentum at which this happens, and with my chiral chemical potential, I could estimate it to be something like this, 10 to negative 7 MeV or so, and of course that changes depending on the magnetic field, the conditions of the gap, and everything. The most interesting thing is that it is generating unstable helical modes. Of course, then when they enter the plasma, regular plasma without mu5, and by the way, when it's feeding on mu5, it's actually eating up that value of mu5, decreasing K star, and eventually disappears. So it's not going to exist forever. But if it enters the regular plasma outside, essentially then it propagates potentially as circularly polarized waves, and perhaps we will even see it on Earth, because it will be possibly primarily in the direction of the emitting jet. So these are, if you consider the numbers seriously, these will be the ways that span the frequencies from the radio to near infrared range. So that's actually something that you could literally see in the telescopes and actually measure. And you could find also how much energy is there. And in fact, within this meters cubic volumes, you will have a substantial amount of the energy which is potentially comparable with the amount of the energy needed to produce fast radio bursts. So the idea is that it is possible to feed the fast radio bursts with this mechanism from chiral plasma stability and potentially explain that physics that to this day remains not fully understood. Of course, there are, one more minute or not? So potentially, of course, there are many gaps in my arguments, and I want to point your attention to those. When I was discussing the chiral charge and electron positron pair production induced by those photons, I didn't really take carefully into account how the interplay happens. Essentially, I considered them more or less independently. Hope is that that is okay because the chiral production happens so rapidly. The chiral flip rate I took from the literature in the plasma without strong magnetic field, and that is, of course, a strong limitation. However, because of strong magnetic field and constrained kinematics of the motion, I would assume, in fact, that there will be a suppression of that gamma, which will give me a boost in the chirality production. So if that hypothesis is true, that will be interesting to verify. This remains to be an open problem. The role of inverse magnetic cascade and turbulence in that plasma when the instability develops, we know that in cosmology it plays a big role. It's not clear we have enough time for all of that to fully play out in this context, so that is a question to be addressed. Self-consistent, of course, dynamics of the plasma in those gap regions should be studied a little more carefully using some perhaps plasma codes. And of course, the energy transfer of that energy into fast radio burst is an open problem. So in summary, perhaps I don't want to repeat the statements, all of them at once, perhaps just to say that anomalous chiral physics potentially has plays a role in magnetospheres of magnetars, producing chirality that in turn feeds into a fast radio burst. And with that, I think I probably want to stop.
Thank you for the talk. So in the beginning, when you described how this magnetosphere is formed, you started with having surface charge densities. Of course, the whole star is neutral, so how should I imagine these? Are there like domains of different charges?
It's a redistribution of the charge. It is neutral. If you look more carefully, there are pluses and minuses. But locally, large field is all you need.
Yeah, and that's exactly what I wanted to say. So how local is that?
Basically, it's macroscopic. The star is 10 kilometers, and the plus and minus, I believe it's quadruple distribution of the charge. So roughly speaking, they are separated by kilometers in distance. So you see minus, plus, minus, plus.
Okay, so my question is about the chiral free plate. So I'm always concerning about that the magnitude, and so my question is there any well-defined field theoretical definition to compute that quantity? For example, could be put to the lattice QCD simulation.
Calculate
chiral flip rate.
The chiral flip rate, right,
yes.
Right. Actually, I was just discussing with Gerger yesterday that problem that I don't know if it were calculated anywhere on the lattice and even how to calculate it on the lattice. That field theoretical calculation seems pretty convincing in the ultra-relativistic regime. They actually revised this problem only, what, like 2 years ago, because the old estimates from the 80s,
yes,
did I go through it already?
Some parametric, the estimate is okay, but what I mean is the actual world identity is deformed, and then it is approximated somehow. And so already you have to introduce some approximation to introduce that quantity.
Yes, you do the approximation easily at large momenta, because at large momentum the fermionic state is almost left-handed or almost right-handed. So in this ultra-relativistic regime, that's precisely what I was saying. They seem to be pretty convincing because in this regime you have nearly perfect chirality. So if you have left-handed, there is only a very, very tiny amount of right-handed admixture, which is m squared over t.
But probably the Kubo type formula is not known, right?
It's not a Kubo type formula. Actually, they did, I quoted on the one paper. This paper actually uses chiral kinetic theory. The other paper, there is a companion paper, which is long PRD paper with a lot of derivations, uses field theoretical approach. Sorry? No. That's why they revised this, because they actually considered QED interactions. And the QED interactions suffer from some infrared singularities, and that's why here you see parametric enhancement from alpha squared to alpha. That's due to this infrared issues.
Thanks for the talk. I'm curious about the effects of a new phase within the magnetar for this electric field parallel. If this could affect the values of the estimate you have given us.
Right. The interior of a neutron-style magnetar could have essentially almost anything. Outside of this star, in this magnetosphere, there is almost no chance to form anything else but electron-positron pairs. The mechanism for the production is essentially the conversion of the photon in the presence of a strong magnetic field into electron-positron pair. If you try to consider anything else, proton, antiproton, that is 2,000 times heavier, and in terms of production, it's absolutely negligible. So there is only electron-positron pair that forms, at least initially, in the gap. And you could only rely on the electron-positron plasma in this context. What is happening inside, I don't really know. And in fact, I don't think it will affect the magnetosphere at all.
Could you show again the scale of for fast radio bursts, that calculation at the end you show the energy? So only for me, because I don't remember very well what is the scale of these energies, but
They are comparable to this number, but the thing is, let me tell you this, that very often how it's estimated, it's also not reliable from the observations, because often they calculate the flux of the energy in a certain direction and then generalize it as if it were uniformly going in all direction, which we know it might not be true. So in principle, these are large enough energies if you collimate most of it within the jet.
I see. And you expect 1 MeV, so is some hot star still. So
This is
more or less.
actually even a little bit less than typical temperatures in magnetospheres. In fact, they probably go up to about 6, even 8 MeV. So this is a rough estimate.
I see. I thought that was less, was 10 to 8. So, but okay, but that's fine. Thank you.
This is the numbers that I see all the time in the context of magnetars
I
discussed.
thought that was KeV. Okay, that's fine. Thank you.
Quick question?
Can the rotation of the plasma also help in creating this kind of behavior?
Rotation is critical for these gaps to form, because if you don't have rotation, in fact, you wouldn't have this loss of the charge as much, and maybe you would have just stationary magnetosphere. The rotation is actually playing a critical role, because you develop this deficit of charge and currents basically all the time. In fact, that simulation I briefly showed, they even argue about the quasi-periodic formation of these gaps. So more or less on regular intervals, they will happen. Sorry? No. There is no good understanding of the full dynamics and the emission of magnetars.
Let's thank Igor again.
Oh, I need to give this away.